Today we are going to see some applications of Riemann integration. So far we have seen only the theoretical development of integration, that is, given a nice function f defined on an interval ab, what does it mean to say integral a to b fx dx? The meaning of this symbol we have explained in the previous lectures. Well, that is an abstract mathematical formulation. As far as history is concerned, Riemann integration was known to people much earlier than Riemann. The sole purpose was to find areas of certain shapes or volumes of certain shapes. So today we will see that with the mathematical rigor which we have injected in the theory of integration, how can it be used back again to solve those kind of problems. So first of all, let us go to the motivating factor of Riemann integration, that suppose I have a function f defined on closed interval ab to r. To be on the safer side, let us assume f is continuous. You then already know, because of our previous lectures, that every continuous function is Riemann integrable. Now the function, let me also assume that f is non-negative. Well, for the purpose of integration, that is not needed. All you need that your function is a bounded function. Then you can talk about Riemann integration of the function. It's a different matter whether the function is really integrable or not. But the Riemann integrable functions are necessarily bounded functions. Now here I am taking an extra assumption, f non-negative. Then let us say the picture looks something like this is the point A, this is the point B, and let us say this is my function f. This is fx. Now let us concentrate on this area. This is the area I am interested in. I want to find the area of this region. Call this area A. Intuitively you know that there is something called area of this shape also. So then if P is a partition, that is, it's a collection of finitely many points, let us say xn, that is equals to B. So this is a partition of the closed interval AB. Then I form the sums UPF. I can also form the sum LPF. I know what is the connection between these two. I know that this is bigger than or equals to. Now, if A is the area, then the kind of picture we have drawn for UPF and LPF, that is, UPF is always made up of the bigger triangles which goes out of the graph, and LPFs are made up of the triangles with lower height which is below the function. Okay? Then if A is the area of the region, then I also know that this is true for all partition P, right? Because UPFs, again I will repeat, are made up of rectangles whose heights go above the graph of the function, and LPFs are made up of rectangles which lie below the graph of the function. And hence it follows that UPF must be bigger than or equal to the area between the function and the axis, that is the quantity A, and this quantity is certainly bigger than or equals to LPF. Now since f is continuous, it is also Riemann integrable, and hence this is also known to me that UPF is bigger than or equals to integral a to b fx dx, which is again bigger than or equals to LPF. Now, as norm P, if I take to be supremum of delta xi, supremum over I, and then limit norm P going to 0, it can be shown UPF is same as limit norm P going to 0 LPF. This is not very difficult to show, turns out to be integral a to b fx dx. Intuitively, the meaning is the same, that you go on taking finer and finer partitions. See, norm P means what? It is the maximum possible length which appears as the subintervals. Now, if you go on taking finer and finer partitions, then the lengths, maximum length of the subintervals are going to decrease heavily. Now, you go on choosing these finer and finer partitions means that norm P's are actually going to 0. If that happens, then UPF converges to the integral of the function, so does LPF. Now, this implies then, by sandwich theorem, that A must be equals to integral a to b fx dx. Okay? So, this is in a way defining the area between the graph of the function and the axis. Because to start with, it has not been defined. We know only the areas of rectangles, triangles and things like that. Now, if I have a weird shape which we had, if we go back at the previous thing, this is a very weird kind of a shape. What do you exactly mean by area of this region? Well, we have got a meaning of that. That area is actually defined by this integral a to b fx dx. Now, I want to find area between two curves. Is that possible? So, let us say situation is this, that f, g, both are continuous functions on an interval a b. These are continuous. Another given condition is fx is bigger than or equals to gx for all x in the closed interval a b. Then the area between the curves, if I call it a, that is defined as integral a to b fx minus gx dx. Okay. So, in the earlier case, what happened is, if I take the function gx to be the x-axis, if the graph of the function is just the x-axis, then the previous case actually follows from this case. Now, let us try to see some examples. Let us first try to find the area between two curves. One is y equals to x to the power 4 minus twice x square, and the other curve is y equals to twice x square. What is the variation of x? Well, I will say minus 2 lesser equals to x lesser equals to 2. Let us first try to have an idea of these curves. How do they look like? Then it would become easier for us to calculate. Now first note that what are the points of intersection of these two curves? That is, suppose I put twice x square equals to x to the power 4 minus twice x square. This would imply that x square into x square minus 4 equals to 0. That would imply x equal to 0 or plus minus 2. Now if I put x equal to 0, then I get y equal to 0. So 0, 0 is one point of intersection of the two curves, and the other points are 2, 8, minus 2, 8. These are points of intersection. Now, I look at the curve y equals to twice x square. What kind of a curve is that? How does it look like? The first of all, if I look at y double prime, that is 4, that means the curve is always convex, and y prime, that is 4x, which is bigger than or equal to 0 if x is bigger than or equal to 0. And since it's an even function, the curve is actually symmetric about the y-axis. And then it is very clear how do the curve actually look like. So I will draw it here. This is 2, minus 2, 2. Then the curve looks like exactly like this. This is the curve y equals to twice x square. Now comes the second one. So I will try to draw both the curves here so that the difference I can make out. One is x-axis, the other one is y-axis. I already know y equals to twice x square looks like this. This is minus 2, this is 2. Now I concentrate on the next curve, which is y equals to x to the power 4 minus twice x square. Notice that this is also an even function, so this curve is also symmetric about the y-axis. First the derivative, that is y prime, that is 4x cube minus 4x, that is 4x into x square minus 1, which is less than 0 if 0 lesser equals to x lesser equals to 1 and bigger than or equals to 0 if 1 lesser equals to x lesser equals to 2. So the function first up to 0 to 1, it is a decreasing function, and then it increases. Now I look at y double prime, that is 12x square minus 4, that is 4 into 3x square minus 1. This is bigger than or equal to 0 if x is bigger than or equals to 1 by root 3. Notice I am just concentrating on the right hand side, that is positive x, because it is symmetric about the y-axis, so the negative side of the x-axis I can take care of the positive side. Now from this information it implies that the curve y is convex if x is bigger than or equals to 1 by root 3. Before that point it is concave, and then the drawing of the curve becomes very easy. I would say that it looks something like That is one side. Second side looks like, something like this. Well, how do I know the curve is, one curve is always less than the other? That is very easy to check. Let us just check it here, that I want to look at twice x square minus x to the power 4 minus twice x square. That is 4x square minus x to the power 4. That is, so taking x common, this is x square into 4 minus x square, which is certainly less or equals to 0. Well, this is certainly bigger than or equals to 0, as minus 2 lesser equals to x lesser equals to 2. That means the curve y equals to 2x square lies above the curve y equals to x to the power 4 minus twice x square. And now if I want to calculate the area between these two curves, which is this area, this is the area we are trying to find out. Which is easy by our previous formula. This is integral minus 2 to 2 twice x square minus x to the power 4 minus twice x square dx. Now from the standard formulas of integration, you can very easily see that this integral can be done. I mean, it's just a polynomial, and integral of x to the power n is x to the power n plus 1 by n plus 1. So using that, what I will get is this, that this is minus 2 to 2 4x square minus x to the power 4 dx, that is 4 by 3 x cube from minus 2 to 2 minus x to the power 5 by 5 from minus 2 to 2. Now this, you just put the values, the answer will come out. We don't want to do the exact calculation, but this is the way you can find area between two curves if the curves are given to you. Now let us go to another example. This is slightly different than the previous one. So this is example 2. The problem is to find the area between the curves x equals to 3y minus y square and x plus y equals to 3. Now let us try to see which curve is above the other one. So for that, well, first I need to find the points of intersection also. Let's try to do that first. So 3y minus y square equals to 3 minus y. This implies y square minus 4y plus 3, that is equals to 0. This implies y minus 3 into y minus 1, that is equals to 0, implies y equals to 3, y equals to 1. But if y is equals to 3, then I get x to be equals to 3 into 3 minus 9, that is 0. So one point is 0, 3, and the other point is, if I put y equals to 1, then x equals to 3 minus 1, that is 2. So another point is 2, 1. So these are the points of intersection of the two curves. Now to see which curve lies above, let us just compare, that is 3y minus y square minus 3 minus y. that is 3y minus y square minus 3 plus y, that is minus of y square minus 4y plus 3, that we know is minus of y minus 1 into y minus 3. Now if y, now question is where do y lie? If y lies between 1 and 3, then what do I get? I get y minus 1 is non-negative, this is bigger than or equal to 0, but y minus 3 is less than or equal to 0, but there is already a minus sign there, so the whole quantity is bigger than or equal to 0. So this implies the curve y x equals to 3y minus y square lies above the curve x equals to 3 minus y. Now to calculate the area between these two curves, what I do is I just look at a equals to, I look at the variation of y here instead. It is between 1 to 3, 3y minus y square minus 3 minus y dy. This is the area between these two given curves. Here, instead of y equals to fx, I am rather looking at the curve x equals to gy. That can also be done. Okay. So this was what all I wanted to talk about, the area between two curves you can find out by integration, which is certainly expected because integration was devised to find area between an axis and a function. Here the axis you are replacing by another curve and trying to find the area between these two curves. So we have seen examples of two such curves. Now let's go to a different topic, again applications of Riemann integration. Now as another application, we want to find certain volumes using Riemann integration. Well, the basic idea is as follows. We start with the simplest possible, the three-dimensional object. What is that? A cube, certainly. Well, I take sides of different length, that is not exactly a cube. So these are the axes. I am just trying to demonstrate what is the idea. So let us say this is one side whose length is a, so this is the origin. This is one side whose length is b. I form the rectangle, which is certainly not three-dimensional, it's two-dimensional. I take this height, this is c, and now I got something three-dimensional. Let us look at this, and I want to find the volume of this. So what exactly is the method? Well, what I do is I come to a distance x here and I just pass a plane which is perpendicular to the x-axis through this body. Just slice it the way you will cut a bread, exactly the same way. So I put a plane passing through this point. So this plane now is going to intersect the body, right? It will intersect the body in a rectangle. You can see the rectangle, this is the rectangle I am getting. So it's a plane which intersects the body. This rectangle which I have formed by cutting the body through a plane at the point x has got an area which I call AX. So this shaded portion has area AX. Can I calculate this AX? Well, I just need to know how to find area of a rectangle. Well, here one side of this rectangle is B, the height is C, so area of AX is BC. Well, you can say it's something special because the area does not depend on x. Whatever x you take, you get the same area, which is Ax. Well, that's good for us. Now I want to find the volume of the total body, and I know the total volume actually is, all of you know that, I don't need integration for that, total volume is ABC. I want to see that how this total volume comes from integration. So what I do is, now I know the area of the slice Ax. This Ax, which is the area of this plane, is called a slice. Now I just want to sum up the areas of this slice together by varying x. But now you would say, how do I sum up? To sum up, I need certain quantities, 1, 2, 3, 4, 5, 6. But here I don't have it because x is varying continuously. But Riemann integration is an analog of sum. So what I do is, instead I just look at integration 0 to a ax dx. Just think of this integration as a sum. It is sort of a, I would say, continuous sum. So I am just continuously summing up all these ax's together, integrating from 0 to a. What do I get? Since ax is constant, it is integration 0 to a bc dx. But bc is a constant, so it comes out of the integral. So it is bc times integration 0 to a dx. But that, by our formula of integrations, which you all know, is ABC. See, what I got back is the total volume. Well, this is the idea behind the volume by slicing. That means, given the body, I take a plane which is perpendicular to the x-axis. Through that plane, I cut the body. I get some section of the body which is two-dimensional. Suppose I can find its area, call that Ax. Then just integrate that Ax over a limit of x from where the body starts to where the body ends. So the general method is called finding volume by slicing. So suppose a body is given to you. To find the volume of a solid, bounded by two parallel planes, perpendicular to the x-axis, at, let us say, x equals to a and x equals to b. So the picture of the body, let us say, looks something like let us say this is the body I have, which is not as symmetric as the other one, and I want to find the volume of this body. So these are the planes A and B, so it is bounded by two planes. I want to find the volume of this body. So what I do is, I take a partition P first. P equals to x0 less x1 less x2 and so on. And let us say at x equal to t, the area of the slice is at. So it would look something like this. So this would be the area of the slice inside the body. It is at the point x equal to t. Okay, I am going to continuously sum them up. But why should that come? Well, you can observe one thing, that minimum of AT, well, to make things correct mathematically, let me also use some convention, some assumption I need about AT. I don't want my AT to be a very bad function. So assume AT is a continuous function of t. In most of the cases, you will have these assumptions satisfied. Because if some weird body is given to you, this AT can be quite a funky function. You don't want that. And then notice that minimum of AT, where t belongs to xi minus 1 xi times delta xi, is certainly lesser equals to the volume of the body when t varies from xi minus 1 to xi, I call that delta Vi, which is certainly lesser equals to maximum of AT when t belongs to xi minus 1 xi times delta xi. So this in particular would imply that LP AX, that is the function, lesser equals to the volume lesser equals to UPAX. But this precisely implies integral a to b AX dx is equals to V. Well, here I have written AX to show, just to mean that A is a function of X. The correct notation would have been LPA is lesser equals to V, lesser equals to UPA. Just to emphasize that it is a function of X, I have written X there. I hope this doesn't create any confusion. But ultimately this would imply then that integral a to b AX dx is equals to V. Now let us see whether this leads to something correct and which we already know. So the next example we take is sphere. Notice that to find the area of a cube, we need to know area of rectangles. Using that, by the method of slicing, we can find the volume of a cube. Similarly, if we want to find the volume of a sphere, it is reasonable to expect that if we know the volume of a disk, using that perhaps we can manage. Because if I slice a sphere by a plane, what I will get is a disk. And we know the area of a disk. We started with that. Any disk of radius r has the area pi r square. I am going to use this to calculate the volume of a sphere. Anyway, given a sphere of radius r, we know that its volume is 4 by 3 pi r cube. I want to test whether I get it through this method of slicing. So let S be my sphere of radius r. Now it looks like this is a sphere of radius r. What I do is, this is x-axis, I come to distance x, I pass a plane through this which is orthogonal to the x-axis or perpendicular to the x-axis, that would produce a disk here. I need to know the area of this disk. So this is my AX in this case. This is AX. So what is this area? I need to know the radius of this disk. That is easy to find out because this distance is R. I just need to know this height. Okay. Now the base is X. I can apply Pythagoras theorem. This would imply the radius of the disk is square root of R square minus X square, and hence AX is equals to, I know area of a disk is pi R square, so it is pi of square root of R square minus X square whole square, that is pi times R square minus X square. Now how much X varies? It varies certainly from minus R to R. This is minus R here, it goes up to R. So I just look at this integral then, integral minus R to R pi R square minus X square dx. This should be the volume of the sphere. Well, this turns out to be pi R square X from minus R to R minus pi X cube by 3 from minus R to R. What do I get? I get pi R plus pi R cube, then minus pi into R cube by 3 plus R cube by 3. What I get is 2 pi R cube minus 2 pi R cube by 3, that is 4 by 3 pi R cube, which matches with what we already know. Now, our method shows that to find the volume of a body, you don't exactly always need to know that the exact shape of the body. Certain information about the body is actually good enough. For example, suppose you know area of each of the slice, then by the method of integration you can find the volume of the body without knowing exactly what the body looks like. That is demonstrated in the next example. So let us say the base of a certain solid is the disk x square plus y square lesser equals to s square. Suppose I also tell you that each section of the body by a plane perpendicular to the y-axis is an isosceles right triangle. Is an isosceles right triangle. Means what? It means this triangle has two same sides and the including angle is 90 degree. Then the point is to find the volume of the body. Well, first we will try to have some idea about the body. We don't know the exact shape, but certain things I know certainly. So let us say this are the axis. I will rather say now that this is the x-axis, This is the y-axis. This is the base, which has been told that is a disk. Okay, fine. Now what has been given is that if I come to a distance y, then this is a right triangle. It means it looks something like this. Okay, so the triangle what I am getting, it looks, I will write a bigger picture here, than this one. This angle is 90, and then this one. So this is actually, instead of AX, this is my AY. I need to know the area of this slice. This slice is in the body. I don't know the exact body. All I know that this is a slice. So I want to find this area. Okay, fine. Now this is y, the total distance. This is the center. From center to this distance is y. And the other thing what I need to know is that the height and the base of this triangle. So question is, what else I know about this? Let us say this portion, I don't know exactly what is this, that this portion is x. Now we have the following picture of the sections of the body. We don't have the idea about the full shape of the body, but what we know is that the base of the body is a disc, and I have this triangle drawn here, which is a section at a distance y. So this distance is y. That's why I call this AY. So obviously my intention is finally is to integrate over y's. Now this length I call it x. That means this other portion is also x. So one side is 2x. Since it's an isosceles triangle, the other side is also 2x, and hence the area of AY I can easily find out. It is half times 2x. What is the height of this triangle? Since one angle is a right triangle, I know the height is also 2x. Since one angle is 90 degree, what I get is half times 4x square, that is twice x square. Okay. Then what I want to know is the volume, which my formula by slicing would be given by integral from minus a to a, because y is certainly varying from minus a to a, ay dy, that is integral minus a to a twice x square dy. Now the variable is x square and I am integrating with respect to y. It cannot be done, but if you check where is x, x is actually a point on the disk. Now I have the equation of the disk, that is x square plus y square equals to a square. So through that equation, given x square, I can find it in terms of y. So it is integral from minus a to a 2 into a square minus y square dy. And you can see that this equation, this integral can also be very easily calculated. One is a square times y, other is y cube by 3, and so on, and the limit is also known, so you can get the full volume of the body. But the point is, I don't know anything about the shape of the body. It can be very weird shape. All I know is how do each section of the body looks like, and from that I could calculate the area of those sections and then integrate over those sections. That is the method of slicing that gives you the volume of the body. The next topic is volumes of solids of revolution. Well, here again we will use the method of slicing, but in a slightly different way. The setup is this, that suppose I have graph of a function again, AB, and this is my function fx. Then I get a plane region which is this. Now what I do is I rotate this region about the x-axis, in this form. If I do this, it will form a solid which will look like this. Right? So we want to find the volume of this solid. Now the idea is again the method of slicing, that if I look at the slice here, what would be the area of this? Well, then the slice actually is a disk, because the whole volume is rotated, so it forms a disk here whose radius is fx. This height is fx, so the ax in this case turns out to be pi times fx square. And then by the method of slicing, which we have already done, the total volume of the solid of revolution is integral from a to b pi fx squared dx. Again, let's try to check how to use this. So I look at the example. Again, I will take the example of sphere, because the volume I already know. So consider the sphere, let us say of radius r, x square plus y square plus z square equals to a square. Then what I do is I view it in the following fashion, that I look at the disk of radius a. This is a disk of radius a, and I rotate this chap, around the x-axis and try to see what do I get. Well, here the slice again would be a disk, but what is this height? If this distance is x, this height which I called fx, that is y, that y satisfies y square plus x square equals to a square. So this would imply that y equals to square root of a square minus x square. Okay. So in this case, ax, according to my formula, pi y square, that is pi times a square minus x square. And then the total volume is integration from minus a to plus a pi of a square minus x squared dx. So we calculate this. This is pi times a square x minus x cubed by 3 from minus a to a. If I put it, I get pi times a cube plus a cube minus a cube by 3 minus a cube by 3. That is pi times twice a cube minus twice a cube by 3, which is 4 by 3 pi a cube. We know that this is the volume of the sphere. So there are actually two ways I have found out the volume of sphere. One is the method of slicing. Other is a slight variant of it, that is by using it as a surface of revolution. So the idea is you just take upper half of the disk, rotate it about the x-axis. What you get is a sphere, and you want to find the volume of that. Then the method of finding the volume of solids of revolution can be used. This is precisely what we have done. This height y actually is playing the role of fx. Then this is actually my pi fx square. And then I have used the integration of this with the variation of x. What I get is the volume of the sphere. So we have seen some applications of Riemann integration. We will see some more. One most important one would be to find length of a curve. For example, if you have a circle of radius r, then we know that the length of the circumference is 2 pi r. We will see how by integration one comes to such conclusions. That we will continue with.